Function systems today, or at least leading up to it. I'll start out with a little review from last time, and then move on to some basic metric space and topological things that we need. And I'll talk about this space, which is where we'll be for most of the semester, and then we'll properly define iterated function systems and see where we'll go in the future. So a few ideas from last time, we really briefly described what a fractal was, just something that exhibits self-similarity. And we introduced the idea of a metric space and affine transformations and similitudes. So if you remember, a metric space is just a set X with a nice notion of distance defined that satisfies these basic properties. Affine transformations are, if we let, well, one example would be if we let A be a matrix and then X would be your vectors. If we just scale, translate, and shear, where these different R1s and R2s would shear it differently in X and Y directions if they were different values. And a similitude, which is the case where R1 equals R2. And so that's just rotations, translations, and scales. It preserves angles. So our next thing that we'll talk about is completeness, closure, and compactness. But before that, we have to do another C, which is Cauchy sequences. So basically, a Cauchy sequence is just a sequence of points where, in a metric space, where the points get closer and closer together as you get farther in the sequence. So, but that doesn't necessarily mean it converges, because it could converge to something that's outside of your defined set. But if we talk about a complete metric space, is a metric space which every Cauchy sequence converges. And some...
You made it further than Emily did before
I think he's talking faster.
And so the one that we'll play the most is just the real, the set of real numbers in n-dimensional space with the Euclidean metric. The complex plane with the normal metric, or the Riemann sphere, which we talked briefly about before, the spherical metric is also a complete metric space. Okay, so this is the main point of most of the project, is a contraction mapping. So a contraction mapping, I mean, that's the formal definition. It basically, it takes 2 points, or well, any 2 points in the sequence, or in the space, and brings them closer together. So since S is less than 1, the distance between the images of the points is less than the distance between the original points. So we're kind of shrink them down. And S is the contractivity factor, which will also play a big role. This is just sort of an example. Like if we start with in the white circle, we have these 2 points here, X and Y, and then the smiley face, we'll call him George. And if we shrink them, all relative distances are also preserved, so you can see like everything is relatively the same distance away, just less. So that's a contraction mapping. Okay, and this is just an actual numerical example. So if this is our affine transformation with A, X, and B, it takes this triangle and it will scale all the X values down by 1/2 and shift them not at all. So we notice that this bottom part here gets cut in 1/2, and then the Y values will be cut in 1/2 but shifted up by 1/2, and so it pushes our triangle here to here. So if we take the one we just did, and then we maybe apply another contraption mapping and take the union of their images, then we might get something like this. So here we just literally just shrunk it down into the corner, so it's just half the triangle it was. And if we apply another one and take the union of its image, we get a third triangle. And this may look somewhat familiar to people. We'll get to it later. It's foreshadowing. So this is just a really basic thing that we'll need later, that the composition of two contraction mappings is also a contraction map. It's really basic because it basically falls from the definition, but I just like to put it there. So this is the big idea of the contraption mappings. So basically that every contraption mapping on a complete metric space has one fixed point, which is given by, if we take our contraption map and nest it with itself over and over and over and over again infinity times, that's going to be our fixed point. And so this is sort of an example. If we take this circle and we cut its radius in half each time and just shift it up by the radius, we shrink shrink, and we eventually reach this fixed point at the top. So now we're going to talk a little bit about topology, really basic things. So a set is open if basically, if you can pick any point in the set and there's a neighborhood around it that's still in the set for any arbitrarily small epsilon. So you can kind of see this like a ball of radius epsilon around the point x. Sort of a good definition is it's a set that doesn't contain its boundary, because if you were to have a set that contained its boundary and you picked the point on it, you couldn't have a neighborhood around it that was still in the set. And then it's closed if it contains all of its limit points. So for instance, like any closed interval on the real line is closed, because if you take any sequence in there that contains only those values, the limit point has to be in there. You can prove that, but it doesn't matter. And another thing that you can show is that, like, open is not the opposite of closed. You can have sets that are closed and open, or neither, but those also aren't important to us.